We're in the process of move. So we'll be here one more week, sort of, transients. See, I know they self-destruct before then, or not. It's getting close. Walking into that men's room this morning, oh my God. Anyway, right. But we'll have our office hours here today. My very stark office. All right. Very good. All right. So let's see. Last time we were talking about how various ways we control quantum coherence in matter, thinking about the atoms in multi-photon processes, which is a very, very important technique that we use all the time. And in particular, if we want to think about encoding quantum coherence into levels that are stable, that are in, say, the electronic ground state, so that they basically don't spontaneously decay, we can do that through a two-photon transition like this, which we call a Rahman transition. Okay? And what we showed last time is that, using our equations of motion with adiabatically eliminating the excited state, then when we're sufficiently far off resonance, that's to say the detuning is very big, not only compared to the line width, but also compared to the Rabi frequencies, then we have effectively coherent driving between these two levels. Okay? And so it's an effective two-level system, yet again, with now my pseudo-spin, spin up and spin down, being these two levels. Okay? And so we think about it as basically control of a two-level system, yet again. And there is an effective Rabi frequency, the two-photon Rabi frequency, that depends on the electric field strength of each of the lasers and the detuning. Okay. The Rahman detuning depends on how close the difference. So if we might say we're on Rahman resonance if the difference of these two laser frequencies is equal to this splitting. That's not exactly true. It's not exactly correct because of the fact that these lasers perturb these energy levels. And so they will be shifted, light shifted, as we've said. There's an AC Stark shift. And if that AC Stark shift is not equal, then there is some additional detuning. One has to adjust the frequency of these laser beams appropriately in order to ensure you were, say, beyond Rahman resonance. Okay? Right. And we were talking also at the end of last week about this very important phenomenon of dark states, which is an important quantum coherent phenomenon. And the idea there is that I can have a situation where I have, say, shine some laser beams on this atom that has a certain energy level structure, and there are superposition states of these sublevels in the electronic ground state. The electronic ground state, but they don't have to be. But there are two levels that are coupled up to this third level, such that the atom doesn't absorb. And we see that in the fact that the off-diagonal matrix element that would couple this state up to the excited state is 0 when I am in this state. And that is what we call the dark state. Okay, the state is your father. As we also mentioned when you're studying in your homework, and it's something quite interesting, is that if you were to start in some arbitrary state of the system, no matter what it is, pure, mixed, what have you, and you then pump the atom in this way, then ultimately the atom will be optically pumped, as we say, in steady state into the dark state. And that's the phenomenon known as coherent population trapping, or CPT. So ultimately, the system will, absorb and emit and end in this state. But it's a little bit of a crazy thing, because this state is not coupled to the excited state. So how the heck does it end up in that state? Because if it absorbs and emits, it might end up in this state, or it might end up in that state. But how does it end in a superposition of those states? Well, that is a puzzle that we won't really resolve until next semester. But I leave it for you to think about a little bit. Right. Now, we were also talking about population transfer, or coherent, I'll call this coherent population. So I might want to have a situation, for example, where I start, say the atoms were prepared somehow in this state 1, and I want to get them over to 2. Okay? And I want to do that with very high fidelity. Okay? The probability of ending in that state I want to be close to 1. How would I do it? Any ideas? Yeah? I could do a pi pulse, right? A Rahman pi pulse. So I have to choose the time such that the Rahman 2-photon Rahman frequency times the total time of interaction is pi, and then I'll just rotate on the Bloch sphere onto that state. So that's one way I can do it. But suppose there was lots of inhomogeneities. I had a whole ensemble of such atoms, and they were sitting in such a way that one of these levels was shifted relative to the other, right, by some inhomogeneous amount. And I wanted to, with high fidelity, transfer the population from here to here. What would I do? I could do it adiabatically, right? I could do adiabatic rapid passage. And how would I do that? What would be the procedure in that case? Yeah.
Prepare in 1, and then sweep you D2 delta.
Right. So what I would do is I start very far for resonance, or far enough that this Raman frequency, and then I would sweep this through resonance, right? And what I would have in that case, if I looked at the dressed states, that's to say the in the rotating frame, I look at the energy level diagram in this system, I have this avoided crossing, where I start in 1 and I end in 2, right? And that is a process known as stimulated what does it stand for? It's called stirrup. What the heck does stirrup stand for again? Something Rahman adiabatic passage. Maybe the SPI is stimulated.
Rapid.
Yeah. Okay, so this is a process known as stirrup. God, I don't even remember what it stands for. But it's this. And it's used all the time. It's an incredibly powerful tool. You may have heard about, for example, there was an example in recent decade where people have been able to prepare ultra-cold atoms. Ultra-cold molecules based on association of cold atoms. But you want to get those atoms into the absolute vibrational ground state. But it's very hard to do that because there's a lot of inhomogeneity, but through stirrup, they were able to do it. So this is a very powerful tool. What's rapid about this, by the way, in the rapid adiabatic passage?
Faster than the decay time.
It has to be faster than the decay time. And what is the decay? What's sort of the decay rate in this problem?
Natural length.
No, it's actually a much slower rate than that. It's true, it depends on that. So this guy decays with some rate gamma, right? But I don't have to go that fast, otherwise I wouldn't be able to do it. This might be a rate of, some megahertz. I mean, the time scale might be nanoseconds, but this gap is not that big. So gamma is not the relevant time scale. What is the relevant time scale? For the decay, what determines the coherence time in this problem?
1 over delta.
Certainly delta's involved, but it's got to involve gamma too somehow.
Gamma ray.
It's the photon scattering rate, right? And that involves both, what we call gamma ram and the single photon scattering rates. That is to say, this depends something like the Rabi frequency squared over the detuning squared times gamma. Effectively, the rate at which the atom loses its coherence between these two levels depends on the fact that it can absorb and then spontaneously decay. But first it's got to absorb. And the probability of being in the excited state depends on the saturation parameter, which depends on the intensity and the detuning. So to make this work well, I need to have the detuning big compared to the Rabi frequency so that this is small, which is the regime that we're working in. But I still need a big enough intensity that, this gap is sufficiently big, right? So that I can do this adiabatic rapid passage. Okay. Great. Now, another way that has some particular interest and advantage of transferring population from state 1 to state 2 is through the process of what's called dark state adiabatic passage. So as we were discussing at the very end of the last lecture, and now let's take a concrete case of this. Let's say I have an energy level up here. It's some P state and there's some ground state. And let's say this state has some spin angular momentum, say nuclear spin, and it's a total spin 1. So it has 3 sublevels, m equals 0, m equals plus or minus 1, okay? So that's my energy level structure in the ground. So say that there's some level up here which is also F equals 1. It's the excited state. It also has these magnetic sublevels. Then I can say couple from this state to this state with sigma minus light, that is left-hand helicity relative to the quantization axis, and through to this state through sigma plus. Okay, so the two different polarizations, the same frequency. Let's just say everything is degenerate. There's no magnetic field to split them. Okay. We have our dark state. There it is. Now, I want to say transfer population from this state to this state. Okay. I can do that in the following way. I start with my light purely sigma minus polarized. Okay? I mean, I've already optically pumped it. I haven't told you how I've done that into this state. Okay. Now, nothing's going to happen because this state is the dark state. So at this point, my dark state is this guy. Okay. Now, suppose that I adiabatically change the polarization of the light such that so this guy starts on, and now I start decreasing its intensity, and I put on a little bit of intensity of sigma plus. Right. If I make equal, if I start turning this off and turning this on such that they're equal, then what is the dark state at this intermediate time? So this is initially. Intermediate. When these guys are equal, what is the dark state?
The minus state.
Yeah, so it's a state which has an equal superposition with 50-50 with a minus sign, right? Well, let me call it m equals plus 1 and m equals minus 1. Right? And then I turn this polarization off and this guy on. Then what is the dark state there? This guy. And I've done it. But look, I've done it exactly in the opposite way. In a Rahman transition, we think about the transition going from here to here. This is what's known as the counterintuitive pulse sequence. If I want to get the thing from here to here, first I put on this light, and then I put on this light. But if I do it adiabatically, the quantum state of the atom adiabatically rotates in Hilbert space from this state to this superposition state to that state. It's a purely coherent superposition phenomenon. Something you could not understand thinking about rate equations and this level goes to that level at that rate. It's a quantum interference effect. Yeah.
Can you explain? The sigma is a 2x2 matrix, but these plus and
One minus sigma plus and
equal
sigma
one.
minus? Is that what you mean? Sigma plus and sigma minus? What are you talking about?
Yeah, I'm confused that there's L equal 1, but then there's operators operating with the sigma plus in.
There's no operator sigma plus sigma minus. So excuse me, this is atomic physics jargon. This means right-hand circularly polarized.
Oh, sorry.
I'm sorry, there's so many reuses of the word so that means I have a quantization axis, what I'm calling the z-axis, and these are the magnetic sublevels relative to that, right? If I shine, so I have some axis I call z. If my laser beam is right-hand circularly polarized relative to the z-axis, it's called sigma plus. If it's left-hand circularly polarized relative to the z-axis, it's called sigma minus. If I'm propagating in this direction and the light is polarized that way, it's called pi. So pi is when the polarization is along, and so the pi transition is this. That's atomic spectroscopy notation. Yeah?
That particular pi would not be allowed?
This is, yeah, and that's actually related to what is a dark state. More to follow on that. Okay, so you're studying that your homework. Yeah?
So you can simply shine a laser and then turn a quarter wave plate to a
Yeah, and you would, if you were to adiabatically, you know, you'd have to be really good in the labs. I know you're good. Yes, I know you're good. But you'd have to be really good at adiabatically turning those polarizations. But it can be done. Typically, this kind of dark state transfer, adiabatic transfer, is not done through polarization, but think about two different colors, and you have two different pulses of light. So, you know, I call, what I would do is, first I'd have a pulse of light with laser 2, and then a pulse of light with laser 1. And they overlap in such a way such that I'm adiabatically turning this guy off and turning that guy on. So what the shape of these pulses are is important. And so that's why this is a more delicate process. And you typically, unless there's some reason that you really want to, then there are some reasons why you might want to go through the dark state. A much more robust procedure is this. Because this depends on the shaping the pulses just right to stay adiabatic. And this is much more forgiving. All right, cool. Now there's one more quantum coherent phenomenon that's very important in the context of three-level atoms that I want to conclude our discussion with. And that is a process known as electromagnetically induced transparency. Or EIT. Okay. So, how many people have ever heard of EIT? Good number, but not everybody. Anyway, it's a fairly famous effect, and one that is used quite often in particular applications. And it's interesting. So, let's remind ourselves, if I have a two-level atom where I think about a ground state and the excited state. Okay, so this is some ground, this is some excited. And I think about detuning this thing through resonance, then we know that we have, you know, the usual, for a weak field here, if I think about this as some probe, and I ask about what is the response of the atom in the limit where the saturation is low, then I get linear response that looks like a Lorentz oscillator, right? Where I have a Lorentzian line shape associated with the line width of this, assuming there's no other broadening mechanism. So that's the imaginary part of the polarizability as a function of this detuning. I'll call that one delta, you know. And I also have a dispersive line shape, right? So that's the imaginary part of the polarizability and the imaginary part of the polarizability. Now,
That's all both.
well, that's the real part. Right. Okay. So now, suppose I have this third level around. Now let's call it level 2. And what I'm going to do is I'm going to dress the system with a coupling laser. So this is the probe. It's shined near resonance to this transition. In the absence of anything else, we have this usual kind of Lorentzian complex Lorentzian response, like a charge on a spring kind of thing, especially when it's not saturating. But now I'm going to put on a strong coupling laser with a much higher intensity than the probe. And I'm going to put it right on resonance. Okay? So these two levels are now coupled together coherently through this coupling laser. And my goal now is to ask, what is the response of the atom in terms of absorption and dispersion as I sweep the probe? How does the existence of this coupling laser modify the response to the probe? Okay. So what we have to do we want to find out how is the polarizability of the atom, the complex polarizability of the atom on this transition modified by the addition of that coupling laser. Okay. So to do that, the way we've calculated that polarizability is we've calculated what is the induced dipole moment oscillating at the probe frequency, and did that to first order perturbation in the probe electric field to find the linear response, as if it were a charge on a spring. And then from that, remember the polarizability. So now we want to do that. We want to calculate the induced dipole moment at this frequency. Okay. So to do that, what we need to calculate is what is the off-diagonal coherence, because of course the expected value of that dipole moment depends on the off-diagonal matrix element. So what we seek is the off-diagonal matrix element of the atom, rho 3,1, okay, in steady state. Let's say after any transients have died out. Because at that point, there will be oscillation on that transition at the frequency of the probe. Okay. So, I'm not going to go through all the algebra here, but we have equations of motion for this transition, using the effective Hamiltonian. So we use our Schrodinger-like equations for the probability amplitudes that we talked about last lecture. And we would get this is equal to this. So these terms are exactly the ones that we had from the optical Bloch equations, thinking about our two-level system, right? And if I just had this would be the Lorentz oscillator, right? Because I look at this in steady state and I get that denominator that would look like that, which would give me Lorentzian, right? But because of the coupling laser, I have this additional term. Okay? So in steady state, this coherence is equal to that. It is modified through the coupling laser in a way that depends on whatever coherence has developed in steady state on this transition. Okay. So what we need to do now, I mean, if we didn't have this term, this is this. It's the complex Lorentzian, right? This is portion of the electric field, and then I get the complex Lorentzian, which has this kind of dispersive and absorptive response, right? But now we have a modification due to this. So we need to know what is the steady state of rho 2 1. So rho 2, 1 satisfies this master equation, which again we can get from the effective Hamiltonian. And again, we're looking at things in lowest order perturbation theory, only to first order, anything that's only to first order in the probe. So we're assuming a weak probe, but a strong coupling. Okay. So since this will develop to some first order in omega p, this is quadratic, and we can neglect this for the first order. This is strong, and so we keep that term. And so in steady state, what we find is that the coherence rho 2, 1 is approximately equal to omega sub c over 2 delta omega 3, 1. Okay? So, given that, we can plug that back in here. So now, this is an algebraic equation that I can solve. And we find that the off-diagonal coherence between level 1 and level 3 now is approximately equal to the probe Rabi frequency over 2 divided by the detuning plus I gamma over 2 minus the Rabi frequency of the coupling over 2 delta. Just solving this equation. Okay? So, with that said, what that tells me is that the induced dipole moment that I care about its complex oscillating at the probe frequency. Remember that this Rabi frequency is minus the matrix element between 3 and 1 dotted into the probe amplitude in units of h bar. And so what we find, putting that all together, is that the polarizability is equal to the following. Minus the dipole matrix element squared over h bar divided by delta plus I gamma over 2 minus omega c squared over 2 delta squared. Now, again, I emphasize that when the coupling laser amplitude is 0, we get exactly what we expect for our two-level resonance, right? We get this congruence, right? But what is the behavior of this thing where now the coupling is non-zero? In particular, what happens as I go right on resonance, where little delta goes to 0? what happens to this guy?
Goes both the real and imaginary part.
So when delta goes to 0, this gets huge and ultimately completely dominates over anything else, right? In fact, if I wanted to ask what is the imaginary part of this as this guy goes to 0, this guy is going to go like minus something, delta squared over 2 omega c squared over with some other denominators. In fact, as delta goes to 0, well, I get the minus, it's going to have a plus there. This thing is going to go to 0 with like a little parabola. So if I were to sketch, and you can do this for yourself, and you should, what the imaginary part of the polarizability is as a function of delta. Well, way out in the wings, when delta is huge, I still have my Lorentzian, but then right in here, I have a wing one. And right on resonance, the absorption is 0. And that is known as EIG. It is transparency. My material becomes transparent, induced due to the coherence that is created between level 2 and 3 with the laser. It is electromagnetically induced, that transparency is. Therefore, it is called EIG. How do we understand what's going on other than this math? What in the world, why is this system now completely transparent and have 0 absorption right on resonance? Yeah.
So you start thinking, you can think of it as like a Rahman transition when the two beams coupled in.
Well, there seems, yes, indeed, there seems like there would be some kind of Rahman transitions, but why would that make it transparent? And Dave is doing something like this. So what's your idea there, Dave?
It's your idea.
Well, I'm not sure it's the right idea in this context. What are you thinking?
The physics is that there's 2 dipoles that cancel each other out.
Right, indeed. So we can, what this is related to, this must be related in some sense to a dark state. And as Dave remembered from last week, we thought about the dark state in 2 different ways. One way we thought about it was in terms of quantum interference, okay? And one way was in terms of thinking about, in a kind of more physicsy picture of physical dipoles that were oscillating that were out of phase, 180 degrees out of phase with one another. So let's think about this from the point of view of both effects. What are the 2 paths that I can think about as, from the point of view of quantum interference? What are the 2 histories which would make that this atom does not absorb any of the probe photons? So let's draw a picture over here. I have my atoms here in level 1, and I shine on the probe right on resonance. And I say there is no absorption of this photon. How does the atom end up in the excited state coming from this starting here? What are possible histories or paths that can lead to the atom finally ending up in here? Well, one path is obvious. One path is that the atom goes from here to here, right? That's one path. But what's another possible path by which the atom can end up in here, given this kind of energy level structure?
1, 2, 3, 3, 2, 2, 2.
Exactly. There is a coherent coupling where it goes from here, stimulated there, and back up. It's a 3-photon process, and this is second order in this guy, first order in that. And would go from here and end up in here. And those two processes constructively, destructively interfere. Okay? And that is one way of dealing with the dark state. Now, of course, really we have to add all the Feynman diagrams, because it's not just this, right? I mean, it can go up and then up and down and down and down. That's another process, right? And I have to add up all processes because it's not perturbative in omega c. It's only perturbative in omega sub p to really get the full. And all of them added together destructively interfere. So it's really not just, in this case, a 2-path interference phenomenon. It's a multi-slit type interference phenomenon. So a clearer way to think about it is exactly what David's suggesting, is to think about this in the following way. We have this strong coupling laser. So when we have a strong coupling laser, we should not think about these states to low order in this, but to all orders in this. Which means that we should think about the dress states, not the bare states, where the atom is dressed by the coupling laser. Okay? Now, how are we going to think about what those dress states are? Well, what we do is we say, all right, if I was exactly on resonance with my coupling laser, then in the rotating frame of the laser oscillating at whatever coupling frequency is, these two states are degenerate, right, in the rotating frame. So I would have state 2, and I have state 3 and state 1, state 3, and state 2. And these guys are coupled by the coupling laser, right? So this is in the rotating frame. You get that? These two guys become degenerate in the rotating frame, because I have to add a photon. Now, what happens to these two states if I now rediagonalize this 2-level system due to the Hamiltonian that couples them? So I'm going to look at this subspace of the coupled level 2 and level 3 in the presence of the coupling laser. I'm going to have a new basis. The dress states, what do they look like?
Something plus something and something minus something.
That's right. And if I'm right on resonance, this is like sigma x of this 2-level system. So up and down along x are the symmetric and antisymmetric combinations of these qubit states. So my states now are split. I have a plus state and a minus state, where this splitting is given by the Rabi frequency. Okay? But I'm detuned here. If this guy is on resonance for the bare states, it's tuned halfway in between the dress states, right? Because one of them gets shifted up by omega over 2. There's an over, why did I write C? Anyway, one gets shifted down by omega over 2 and the other gets shifted up by omega over 2, right? In the dress states. Okay? So, how do I now interpret EIT in terms of Dave's nice picture of dipoles? So this atom is in the ground state, can be coupled to either this guy or that guy, right?
With the coupling to the opposite.
One is red detuned, and the other is blue detuned. And as you remember, the induced dipole moment is 180 degrees out of phase. Remember the slinky? Thus, these two dipole moments are exactly 180 degrees out of phase, and there's no absorption right halfway in between the dress states. That is the best way to think about what's going on in the EIT. Yes, sir?
Is it incorrect also to think about it in terms of the block vector that goes spin up and spin down, x spin up and x spin down, have 180 degree apart block vectors?
Well, they would. I mean, it's really a question of how those block vectors are oscillating. On the block sphere, in steady state, one block vector will be pointing in one direction, and the other will be pointing the other direction. And that's the block sphere picture of the same thing. That's correct. Right. Now, one of the things that, so that's neat, interesting, maybe. What's it good for? Well, a lot of people have thought about lots of different ways. I mean, the whole hope for a long time is that somehow the problem is you want your cake and eat it too. You want to somehow have the good effects associated with atomic response to matter, but you don't want absorption. So the hope is that something interesting is going on inside this transparency window where I'm not going to get a lot of absorption, but somehow I still get a lot of good stuff. And it's kind of hard to come by, but here's one way that you can come by it. What about the real part of the polarizability? What does that look like in this thing? Well, it's I don't know if that's one of your homework problems or not, I can't remember. I think it might be. But here's what it looks like. So, in the wings, it looks exactly like we had for the Lorentz oscillator, but in this transparency window, and I'll just blow that up a little bit. So here's my transparency window. This is the imaginary part of alpha. And in here, I have this extremely steep slope of the real part, which slopes in the opposite direction. It has a positive slope, rather than there, it has a negative slope. Okay? This is related to what you may have learned about Kramer's Kronig, about the relationship between real and imaginary parts. of the response when you have causality. But this very steep slope in the polarizability means a big dispersive effect. That's to say, the index of refraction of a medium filled with these EIT atoms is really weird. It has this transparent window where the index of refraction is changing very rapidly with omega, or detuning. And what that does means is that you have a group velocity. Whereas the group velocity depends on the dispersion, that is, say, how omega changes with function k in this situation. And with such a strong steep, you can get a situation where the group velocity, the group, is tiny compared to the speed of light. And there was a very famous experiment done at the end of the 1990s, where using EIT, group at Stanford and Harvard were able to slow down a pulse of light to moving 17 meters a second. So you could go on your bicycle and go faster than the light pulse moving. So that was a kind of curiosity, but later it was understood that by adiabatically turning off the light, the probe, the couple, the probe would come to a stop. And the light would be stored in the coherence that is created between these two states. And this is a method for creating quantum memory. That's to say, I can store a pulse of light in the quantum coherence of atoms, and then by turning the coupling back on, release the hounds, my light, and take a single photon back out. So that's been one of the most interesting applications of the EIT. But there are other interesting, more recent interesting applications, including things like the nonlinear response of the system, going beyond this thing about nonlinear optics. And you can get extremely strong effects like binding between photons. You can create bound states, something like a lightsaber. I talk about the dark state, where the photons actually feel one another mediated through the material. So this kind of being able to manipulate quantum coherence in material creates very different kind of optical response, very different than you can get when you think about just classical charges on springs. It's fun for me because that was actually the subject of my PhD thesis, was two photon bound states. It was written that paper was written in 1992, and actually wasn't about EIT though. We didn't have it that smart. But I had this idea about I can use nonlinear response of atoms to make two photon bound states, and that it was finally done in a few years ago. So that was fun for me. All right. Yes.
So the diagram you just erased, the one with states 2 and 3 in the top and 1, we can draw that because our coupling is strong and our probe is weak, right?
Correct. So you mean all the Feynman diagrams?
No, the one after that using the other explanation.
Oh yes, you mean why the dress states? Yes, absolutely. Because the dress states are the eigenstates to all orders of perturbation. It's like doing the Feynman sum of all the Feynman paths up to infinity. Because of that, we can just do the straight up diagonalization, and we do that because we assume the coupling is strong. Yeah.
Also in your lecture notes, I didn't quite understand how you got to the boxed expression for
Here?
the dagger.
doing the algebra. So I just multiply this by this, subtract off that,
No, I
and then divide, and I get this.
Oh, so it doesn't come from the two lines above it?
You mean from, so this, do you understand how this follows from this?
Yeah, that's from.
Yeah, that's that, right. But then this is what we've done in the past, where we said the dipole expectation value as a function of time is equal to the trace of d as a function of time in the rotating frame times rho in the rotating frame. Okay? So everything is done in the rotating frame. This procedure is the same one that we use to get the two-level response.
I see, so you're multiplying the top two lines.
That's right.
You get the third one.
That's correct. All right. Everyone's going to take a deep breath. Okay, ready? We're going to shift gears. That's my equivalent of Carl Cave showing a picture of Iceland. We're going to transition in our lectures onto something completely different. And so, since the beginning of time, known as August 2019, we've been talking about, really the only real quantum we've been talking about is the quantum coherence in matter, induced by electromagnetic fields. But we haven't talked about quantum coherence in the electromagnetic field itself. I mean, we know about classical coherence, but we want to talk about quantum coherence in electromagnetic fields. So the first question is, why do we even need to bother quantizing the field in the first place? Where did it, in any of what we've talked about, do we even have to worry about the fact we've treated the laser classically? Figuring out why the heck we can get away with that. But was there anything in what we've been discussing that required us to include the quantum nature of the electromagnetic field? Not much, except one thing. The spontaneous emission rate, right? I mean, we know that if I now go back to my two-level atom, if I prepared the atom in the excited state somehow, then in the absence of quantizing the electromagnetic field, this state is a stationary state. It's an eigenstate of the atomic Hamiltonian. And so, if there was nothing else, if this atom were completely isolated from any collisions, from anything else, it should stay in that state forever, because it's stationary. But we know that this state is not stable, and ultimately will spontaneously decay. Now, it's an interesting question, and one that I alluded to at the very beginning of the semester, about the degree to which I need to think about that quantumly, and the degree to which I can think about that classically. We saw in our early discussions about the Lorentz oscillator that the Lorentz oscillator will decay if it's oscillating because of radiation reaction, right? So in what way should I think about spontaneous emission as anything different than radiation reaction? Well, that's an interesting question, one that I hope we'll get to discuss a little bit later in a few weeks. But irrespective of that question, we do know that if the atom is in the excited state, quantum mechanics says if that's an eigenstate of the Hamiltonian, it should just forever, probability to be in that state should be 1 for all times. And the only way it can evolve into a different state is if it's not an eigenstate. And it's not an eigenstate because the atom, the zonal Hamiltonian, involves the atom and the field and the coupling of the atom to the field. And we need to think about this part, the quantum nature of the field itself and how the atom and the quantum field couple to one another. So we're going to spend a week or so doing a little bit of an introduction to quantum field theory to get here. Okay. Now, how do we think about that? Well, the quantum electromagnetic field we think about to get to that is that the degrees of freedom are the normal modes of the field. So like a string pinned between two walls, we can think of normal modes of oscillation. And each of those normal modes is a degree of freedom, if we thought about it from the point of view of the string. Each of those normal modes is equivalent, its dynamics is the dynamics of a simple harmonic oscillator. And so to quantize the field, this involves the appropriate way of decomposing the field into the appropriate normal modes and then associating those normal modes with harmonic oscillators and then quantizing each of those oscillators. Okay. There's lots of subtleties involved in that. It's particularly hard and crazy for the in-end field. And we'll kind of sweep some of that under the rug, but in your notes you'll have a kind of full supplement to see the real story. So, what I want to do quickly, and in a way that you may not have seen before, but I think is important, is to just talk about the quantum simple harmonic oscillator very quickly. Okay? Hope it can be done in 12 minutes, but we'll see. Maybe not. So, to do so, for pedagogical reasons and reasons that allows us to be thinking about quantizing the field, we'll start with the classical simple harmonic oscillator. Okay. Mass on a spring. So I got spring, got mass, it has a spring constant. The kinetic energy, and let's say there's a coordinate q, that is its extension away from equilibrium. We got kinetic energy, we got potential energy. We got a Lagrangian. We have the canonical momentum, which is the partial of the Lagrangian with respect to the canonical coordinate, and q dot. We got the Euler-Lagrange equations. And of course, this is the resonance frequency.
Should
Yeah.
your momentum be derived with respect to Q dot?
Yes, thank you. Absolutely. Yes. Absolutely. Right. And then, of course, I can write down the Hamiltonian. I'm doing this really silly thing just to remind you of this procedure because we're going to generalize this to the case of fields. So my Hamiltonian here, I get in terms of the canonical momentum. I have Hamilton's equations. Which tells me that Q dot partial of H respect to P and P dot is equal to minus H respect to Q. Right, this, I'm going to write this as 1/2 m omega squared Q squared. Right? So far so good? All right. And of course, these give me the same differential equations for the simple harmonic oscillator. Okay. Now, when thinking about any physics problem, the first thing one should do is think about the appropriate scales in the problem. Okay? So, if there is some energy scale in the problem, I'll call it some characteristic energy scale. I'm not sure what it is yet. Given that, there are only two other parameters in the problem: the mass and the frequency, right, or the spring constant. So I have the other parameters are, in this case, the mass and the frequency, or the spring constant. So the question now is, what is a characteristic length scale given these parameters at this point? So given some energy scale and given a mass and a frequency, how can I form a length? This kind of thing, I don't know, it's always a thing that students find that, well, this is scary, I don't know what to do, this is not rigorous, what do you mean? But it's so important to be able to use a kind of numerology, but it's really the essence that tells us about the essence of the physics that's going on. So, how would I form out of an energy? Well, there's a number of ways I can look at it. I can say, well, I'm going to say this is an energy scale, m omega squared q squared is an energy scale. So I'm going to set, I'm going to forget about any numerical factors, factors of 2 be damned. I don't really care. It's just a scale anyway. So m omega squared times some characteristic length squared, I'm going to define to be equal to that energy. And so this gives me a characteristic energy scale, omega sub c, in terms of the square root of EC over m omega squared. Okay? And my characteristic momentum scale, anyone have an idea? What would I do? Same thing. But now I'll do it the other way. So there's some characteristic momentum squared over the masses. I'm going to set equal to that same energy scale. Right? So my characteristic momentum scale is the square root of m times whatever the characteristic energy scale is. Okay? So with that said, I'm going to define dimensionless variables. I'm going to define capital X to be Q over the characteristic scale, and capital P to be the momentum divided by the characteristic scale. So these are dimensionless variables. Okay? My Hamiltonian, in this case, is equal to P C squared over M, P squared over 2, plus 1 plus M omega squared XC squared, X squared over 2. And we've, by choice, chosen both of those equal to be the characteristic energy scale. That's how we define PC and XC, right? So this is my, and I can think about this as dimensionless Hamiltonian. Call it little h. We already have the h. Okay, let's look at the equations of motion for the canonical coordinates in dimensionless variables now. Okay, so if I plug in now Q is equal to XC times X, and P is PC times capital P into those equations on the right, I get the following equations. The time derivative of X is equal to omega P, and the time derivative of P is equal to minus omega X, which is a little bit of algebra. Okay, just plugging in the relationships between the dimensionless variables and the dimension-full variables. Those are kind of nice equations. I've gotten rid of things. You see the, I haven't gotten rid of the time scale. We could find a dimensionless time, but I'm going to keep omega explicit. Okay, you see these equations. And of course, these equations I can decouple by taking the second derivative, and that will give me P dot, which is minus omega squared X, or this. And similarly, for P. Taking the second derivative of this, plugging it in. Right? And the solutions to these differential equations are easily written down. So there's the initial conditions. The initial conditions depend on the initial position and the initial velocity, right, in the second order. And you do all that, and you get the following equations. Those are the solutions to those equations with those initial conditions.
The second term in the X equation should be sine omega t?
It should, yeah. So, these, of course, are the equations of motion. The motion in phase space in this problem is the motion on a circle. Right? These are the equations of motion that look, the trajectory is a trajectory on a circle. We can see that easily by looking at the fact that if I take these equations and I look at x squared plus p squared, at any time, that's the same thing as what it was at the initial time. And of course, that is not surprising, because this is just equal to twice the energy in units of the characteristic energy, right? And energy is conserved. So if you tell me the energy, that tells me on which trajectory I move. And the energy determines the radius of the circle in phase space. Okay. Now, it is tradition, but unfortunately a pain in the butt, this damn factor of 2 of where it should go. And in my notes, I have a one-way, and then, oh, I never changed it from 2002 because I'm too lazy and I don't have the original file. But this is a much better normalization so that I talk about the radius here in this way. Now, with that said, so I'm gonna, thus, on my phase space, I'm gonna write this as x over root 2 and p over root 2. Okay. The trajectory, this is a point in phase space, is on a circle in my normalized variables. And the radius of this is given by this energy in units of the characteristic energy. This is undergoing a circular motion with an angular velocity omega. Question. Ooh. Question. Does it go clockwise or counterclockwise?
Clockwise.
Yes. How do we know that? How do we see that? Well, I can just look at this equation. For example, suppose at time t equals 0, I started here. At a later time, the p goes negative, right? So it goes around this way. So if it started at some, if I think about this as both in terms of an amplitude and a phase, I can think about it also initially as having some initial x0 and p0, right? Then the motion of this is such that x of t is equal to a cosine the initial phase minus omega t, and p of t is a sine phi minus. Or, if I like, a cos omega t minus phi, and minus a sine omega t minus phi. Where a is equal to the square root of x0 squared plus b0 squared. And phi is the arctangent of x0 over p0. Now, whenever thinking about oscillatory motion, with oscillations at frequency, some fixed frequency, it is convenient to think about this in terms of complex amplitudes. And so instead of actually, the way I've drawn this here, this is x over root 2, x over root 2 is this, where this is over root 2. And that's how it should be. Okay. So, let us define this as a complex plane for the complex number alpha. Alpha having a real part, x over root 2, and imaginary part, p over root 2. So this is the real part of alpha, and this is the imaginary part of alpha. So what alpha at time 0 has an amplitude and a phase. It also has a real part and an imaginary part. What is alpha at a later time? Well, it is equal to that. You can easily check that because you can write this as this. And you will see, in fact, you plug those in, and this is equal to x0 plus I p0 over root 2 e to the minus I omega t. So, take this, plug in those, you get this. So, we think about this phase plane as a phasor, a complex phasor, which has a complex amplitude alpha. It is rotating in the complex plane at frequency omega clockwise. The real part of that complex amplitude is the position over root 2. And the imaginary part is the momentum over root 2 in dimensionless units as such defined. What about the energy of the system? How is that related to the complex amplitude? Well, the Hamiltonian there, if I look at that, is EC times that, but that's nothing more than the magnitude. So the complex amplitude squared is the energy in units of characteristic energy. Or, as we like to write it, is alpha star alpha. This is all extremely important. It's the harmonic oscillator, you know it, but you may not have seen it in this way. You should learn it, please. It's really important. The main important thing here we learned is that our harmonic oscillator motion, there is a complex amplitude that describes that motion. Because it's always a complex amplitude, because any harmonic motion has some amount that's in phase with cosine and some amount that's 180 degrees out of phase. The parts 180 degrees out of phase has an I. Okay? So these two pieces of the oscillation are known as the quadratures. Because they oscillate 180 degrees out of phase. So when we think about an oscillator, we can say how much amplitude we have in the two quadratures. That completely determines the oscillation. Alternatively, I can say what is the amplitude in phase. Those are that's two different parameterizations for the same simple harmonic motion. Okay? Okay. Thanks for sticking around so we can get to this point and move on to the quantum version. We will be in here on Wednesday, I assume. Use the restroom somewhere else.